Hello, calculus fans. All right, let's say I hand you a bunch of numbers, just call them y1 through yn, and I ask you for what's the average of those numbers. Well, it's really easy to compute that. So the average, we just have to add them all up and divide by however many numbers there are. Well, what if there's infinitely many numbers? So as an example to motivate this, let's suppose that we had a thermometer, sort of think of a digital thermometer, and it records the temperature at any instant in time over a 24-hour period. And then we'll represent that temperature as a function, big T of little t. So little t is the number of hours since we started the experiment. Big T of t is the temperature at that time. So the temperature is a function of time. We want to figure out a way of determining what's the average temperature over this time interval. So generally speaking, let's suppose that we have a function f of x, and we'll say that the function is defined for x between a and b. And we want to compute the average value of this function on the interval from a to b. So we're going to follow the usual sort of game plan that we always have with these sorts of things. We're going to divide the interval from a to b into n equal-sized subintervals. Each of them has a length delta x equals b minus a over n. And on each subinterval, we choose sample points x1 star through xn star in the n subintervals. And then, instead of trying to compute an average of the function, we just compute an average of these numbers, f of x1 star through f of xn star. And if we've chosen enough subintervals, then we can sort of think of this as pretty closely representing the average value of the function. So this average is going to be, well, we just add them all up, f of x1 star through f of xn star, and divide by n. That's because we have finitely many numbers, so it's not really all that complicated. Now let's do a little bit of manipulating. N is the same thing as b minus a over delta x. You should be able to see that from the expression where we have delta x is equal to b minus a over n. So if you solve for n, you'd get b minus a over delta x. Manipulating further, this can be rewritten as 1 over b minus a times f of x1 star plus all the way down to f of xn star, all times delta x. And then we can rewrite this with summation notation. If you have f of x1 star added all the way up down to f of xn star, that can be rewritten with the sigma notation to say that this is the sum, where k goes from 1 to n, of f of xk star. This is the same kind of sigma notation that we always use when we talk about Riemann sums. And that's what we have here. We have a Riemann sum. So as usual, we let n increase, and that gets us a better and better approximation. And in the limit, as n goes to infinity, this is what we get. So we have the limit as n goes to infinity of 1 over b minus a times the sum, k goes from 1 to n, f of xk star delta x. And whenever you take a limit of a Riemann sum, you get an integral. In this case, we have a 1 over b minus a out in front that we'll have to keep around. And this is going to be our definition of average value. So the average value of the function f of x on the interval from a to b is, we'll call it f average, is 1 over b minus a times the integral from a to b of f of x dx. So this right here, that's our new formula, average value of a function. And as usual, we always just have to say that this is how we're going to define it, provided that this limit exists, which means provided the integral exists. Okay, that's all for now.